Within the layer of indexing, remember the purpose of indexing is to reduce page reads and to eliminate bookmark lookups, not for every query, but for the queries that are being used in the 90% of the time. And I found that usually boils down to just a handful of queries. You want to plan your clustered index extremely well because that's the best way to avoid a bookmark lookup. You want to use covering indexes to avoid other bookmark lookups. And use a comprehensive strategy when you're planning your indexes. What I like to do is to analyze a table and say, here's all the columns, here's all the code that accesses it, and actually plan out indexes so an index can be reused by multiple different queries. Both query 1 and query 3 and query 4, for example, might use this non-clustered covering index. So think about it. If we have a clean schema, good, well-written set-based code, and we have good indexes to connect the set-based code or the question with the schema or the answer, then we've already planned to have small, tight transactions, little sips at that water fountain. But if you have a poor schema, lack of set-based code, missing indexes, or maybe lots of non-clustered indexes that all have to do bookmark lookups, no amount of locking hints is going to solve this locking and blocking problem, because the lock is not the source of the problem, it's those long transactions being caused by poor indexes, poor code, or complex schema. So that's why schema, set-based code, and indexing sets you up for good, fast concurrency. And to make sure the concurrency is fast, and assuming that the schema, the set-based code, and the indexing layers are all done well, then you want to make sure concurrency doesn't cause additional problems. So make sure that within your sprocs, the logical transactions, meaning the begin tran and commit tran, that those are as tight as possible. There's no extra code in there. Use the right transaction isolation level. Don't make it any higher than it needs to be. I recommend staying at the default. Consider using snapshot isolation. Keep your triggers fast and tight, and use them only for database enforcement of database rules, not for large business rules. Put the complex code in a stored procedure to validate the data prior to the trigger. Pay careful attention to the physical location of the transaction log, because the transaction log has to be written to and confirmed before that transaction can complete. And focus on TempDB performance, because that's the real bottleneck for SQL Server 2005. So, schema, set-based, indexing, concurrency, if you've done all of these best practices, you do have a well-performing, scalable database. SQL Server Enterprise Edition comes with some cool scalability features, and it's a huge mistake to use those features to try to overcome the lack of a good design in any of the schema, set-based, indexing, or concurrency layers. The scalability features that I believe make the most advantage of a good design would be partition tables, indexed views, and then using Service Broker. And of course, partition tables and indexed views are only present in Enterprise Edition, but Service Broker is there for all the editions of SQL Server. The point of all this is that if you have a performance problem, examine the enabling layers before you try to fix where you think the performance problem might be. For example, many DBAs believe their database has a locking and blocking problem. I would disagree. I'd say they have a schema, set-based, and index problem, and that's showing up as a symptom as locking and blocking. And it's true, third-party applications, it's probably impossible to fix the schema. So you want to just work at the lowest level you possibly can. But I've seen in-house developed databases with a poor schema, and they would love to rebuild it, but they're unable to because they don't have an abstraction layer. So if all of these areas are messed up, the first thing to do, the way that you approach it as a data architect and fix this problem, is to build and enforce an abstraction layer, as expensive as that might be. That will allow you to then refactor and redesign the schema, and then fix the set-based and indexing and concurrency. And when you find yourself in a maze, lost in poor performance, and you don't know the way out because it seems everything is a mess, the abstraction layer is probably your key out. So that's the whole idea of optimization theory, the umbrella idea for a number of areas within the database, and each area has a number of best practices. Rather than just a random collection of best practices, optimization theory states that there are inherent dependencies, and the only way to really benefit from one best practice is to make sure other best practices are already in place. Optimization theory is a framework for performance based on these dependencies, and each layer enables the next layers. So to visualize this, the schema enables queries, enables indexes, means nice, fast, tight transactions, which reduces the overall aggregate workload of the database, and then sets you up for the advanced, more scalable features. Looking back to the overall database system, when the aggregate workload of the database has been optimized, it makes the other components so much easier to work with. For some databases that I've seen, following optimization theory could reduce the workload on that server down to 1/8 of what it's doing right now. Planning effective maintenance plans and SQL Server jobs for a well-designed database is so much easier. And then with a good abstraction layer, writing the data access code becomes an effort in consistency rather than just a mess. So for all of these components, the beginning point of good design is the database schema. And you can download a white paper on optimization theory and other design ideas from my website, SQLServerBible.com.